viewers, good morning. Welcome to Quick Coder. My name is Tulasi. Today's topic is asymptotic analysis. So let's get started. So in the previous video, I have discussed how the algorithm is analyzed using some naive approach. But now I'm saying, so we already discussed what are the problems or what are the disadvantages of analyzing the performance of a algorithm using the naive approach. But now we are seeing how we can overcome that problems using this asymptotic notations. Okay, using this asymptotic notations. So the big idea of this asymptotic notations is we evaluate the performance of an algorithm only in terms of input size. Okay, we do not measure the actual running time. We only measure the performance of an algorithm in terms of input size. Okay, we calculate how the time or space taken by algorithm increases with input size. Okay, we only depend upon input size. That's it. So and now in this video we will take some examples and we will analyze that using asymptotic analysis, and we have three cases. We have three cases on that. One is worst case, one is best case, and one is average case. Okay, we have something like big O notation, big omega notation, and big theta notation, which usually like big O like upper bound, big omega like lower bound, and big theta like average bound. So we will see all these types in this video only. Okay, so let's get started for that. Okay friends, let's discuss the big O notation. Okay, here the function f of n is equal to of g of n. So let's first of all, this is the definition of this big O. This is totally a mathematical formula. I will explain this total with a graph. Okay, let's take some algorithm. Okay, there is some input. As I told, it totally depends upon input. Okay, and there is some time with you. That algorithm runs like this, for suppose. Okay, or else like this. Okay, your function goes like this. This is the function of this, or this is the f of n is the equation of this line. Okay, and you should as I said, the big O notation is like upper bound. You should find some upper bound to this. Okay, you should find some upper bound. So for example, I'm drawing like this, and this is somewhat upper bound. Okay, like c into g of n, and there is some n naught here, where n naught is always greater than or equal to 1, because our input should be at least 1 or greater than or equal to 1. So from here onwards, I started drawing the upper bound of this function c into g of n. This mainly tells us the upper bound, say your algo will not exceed this. Okay, your algo, so how much input size you will take, your algo will not exceed this upper bound. Okay, will not exceed this upper bound. So let's come into the algorithm now. So f of n is equal to big O of g of n if there exists positive constant c and n naught, such that f of n is less than or equal to c into g of n for all n should be greater than or equal to n naught, and n naught should be greater than or equal to 1. So for example, I took an example, f of n is equal to 2n plus 3. Okay, f of n is equal to 2n plus 3. So what I am doing is, here simply, it's very simple, f of n should be less than or equal to c into g of n. That means 2n plus 3 should be less than or equal to c into g of n, some constant into some g of n function. So how can you say that when we write here 3 into n, this will work perfectly? Am I right? So this will work perfectly. So for example, 2n plus 3 is less than or equal to 3n, where n should be greater than or equal to 1. If I place 1 here, 2 into 1, 2, 2 plus 3, 5 less than or equal to 3 into 1, 3. Here our algorithm not works. So let's see, let's change this 3 to 4. Okay, so if I keep 4, 2n plus 3. Okay, 2n plus 3 means 5, 5 less than 4 into. This also not work. So let's take something like 5. Okay, if we take 5, 5 here, 5 into 1, 5. See, 5 less than or equal to 5. So from 5 into n, 6 into n, this all works with this. Okay, so our c is 5, n is 1. Sorry, n is, g of n is n. See, here our c is 5, our g of n is n. So we got some big O notation for this. So f of n is equal to big O of g of n. As we already calculated g of n, that is 1. So big O of n. That's it. Okay. We can also find this c value using just placing, as this is the fastest growing term. So keep n for this 3 also. Like 2n plus 3n, we will get 5. Okay. Okay. That's it about big O notation. And the next is big omega notation. I will explain. Okay friends, there are some more with this big O notation, because as we got g of n as n, we can also write n square, n cube. Okay, like we can also write 2 power n, 3 power n, n power n. So we have many things here. So see this. So our algorithm will have the time complexities to 1 to n power n. N is the input size. Okay, it will not cross this, and it may be multiples of this one. Okay, so it may be root n into log n, or root n into log n, n into log n. So like this, it's only the multiple of these things. Okay, it's only between this range. Now here, instead of n, we can also write n square, n cube, 2 power n, and so on, 3 power n, n power n. But the tightest bound is 1, because up to here, n log n, n square, n cube, these all are upper bounds. But the tightest bound, or the least upper bound, is n. So we always stick to this. These are also correct answers, but we always stick to the tightest bound. Okay, so in the next video, I will explain the big omega notation and big theta notation. Okay, so I hope you understood very well, and thank you for watching.